This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on the fundamental theorem of calculus together with U substitution problems. Our first example is the integral from 0 to 9 of the square root of x plus 5 dx. Now, we have to remember that we have a power rule that enables us to do integrals. So we're going to rewrite the square root of x as x to the 1/2 power. And our next move is to recognize that the integral of the sum is the sum of the integrals. I can rewrite this as integral 0 to 9 of x to the 1/2 dx plus integral from 0 to 9 of 5 dx. What is that power rule? The antiderivative of x to the n is x to the n plus 1 over n plus 1. So 1/2 plus 1 would be x to the 3/2 over 3/2. And we're evaluating that as x goes from 0 to 9. The antiderivative of 5, a function whose derivative is 5, of course, is 5x. We've got to plug 9 and 0 in and subtract, but let's clean this up a little bit. Dividing a fraction by 3/2 is the same as multiplying it by 2/3. So we have 2/3 x to the 3/2 from 0 to 9 plus 5x as x goes from 0 to 9. Plugging in the 9, we're going to recognize x to the 3/2 as the square root of x to the 3rd power. That's where we're going to plug in the 9. X to the 3/2, square root of x first, then 3rd power. That'll make the computation a little easier. Plugging in 9, root 9 to the 3rd power. Here, minus root 0 to the 3rd power. Then plugging in 9 here, 5 times 9 minus 5 times 0. Root 9 is 3, 3 cubed. Root 0 is, of course, 0. 5 times 9 is 45 minus 0. 3 cubed is 27. 27 times 2/3 plus 45. 18 plus 45, which gives us 63. Our next example is the integral from 1 to 9 of 5x squared plus 3x plus 2 all over the square root of x. So is this a U substitution problem? Or do we go directly to the fundamental theorem of calculus? The key is to recognize when there is a common denominator, we can break this up into 3 pieces. Integral from 1 to 9 of 5x squared over root x plus 3x over root x plus 2 over root x. Now what does root x represent? Well, as an exponent, it's x to the 1/2 power. And then you can remember when you're dividing two things with the same base, you subtract the exponent. So 2 minus 1/2, 4/2 minus 1/2 would be 3/2. This will give me 5x to the 3/2. X to the 1 over 1/2 will give me x to the 1/2, and this, of course, will give me x to the negative 1/2. What are we going to do next? Remind ourselves of the power rule. Again, integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. So 3/2 plus 1 is 5/2. X to the 5/2 over 5/2. 1/2 plus 1 is 3/2. X to the 3/2 over 3/2. Negative 1/2 plus 1 is 1/2. X to the 1/2 over 1/2. We're going to evaluate that as x goes from 1 to 9. 5 divided by 5/2 is 5 times 2/5, or just 2. 3 divided by 3/2 is 3 times 2/3, or just 2. 2 divided by 1/2 is 4. And then we're going to plug in x from 1 to 9. Remember, we're going to do the square root first. So 9 to the 1/2 is 3 raised to the 5th power. 9 to the 1/2 is 3 raised to the 3rd power. 9 to the 1/2 is 3. 1 to any power is 1. So those are 1, 1, 1. Easy for us to do. So again, 9 to the 1/2, 3 to the 5th power. 9 to the 1/2, 3 to the 3rd power, 9 to the 1/2, 3. So we get 2 times 2, 43, plus 2 times 27, plus 4 times 3, minus 2 plus 2 plus 4. And we get that 486 plus 54 plus 12 minus 2 plus 2 plus 4. 552 minus 8, or 544. Next we have the integral from negative 5 to 5 of the square root of 25 minus x squared. U substitution does not work here. You may want to let u equal 25 minus x squared, but its derivative, negative 2x, is not there. There is no multiple of x that's going to divide out. So U substitution doesn't work, and you do not know the antiderivative. You actually have to use a technique called Trig Substitution to get it, but we don't need to do that if we recognize the geometry. So looking at this curve, y equals root 25 minus x squared. Y squared is 25 minus x squared plus y squared is 25. What is that? A circle centered at the origin with a radius of 5. So if we draw our picture, that's what it's going to look like. We want the area under the curve, but we only have the upper half. Notice y equals root 25 minus x squared is only the upper half of the circle. And we want the area under the curve as we go from -5 to 5, which will give us this half circle. So y equals root 25 minus x squared is the upper half. Y equals negative root 25 minus x squared is the lower half. So we just want the upper half of the circle, area under the curve as we go from -5 to 5. Area of the circle is pi r squared. Radius here is 5. Area of the entire circle is 25 pi. Of course, we just want half of it. So this integral represents this area under the curve. And we can say that that's 25 pi over 2. So we're able to do that with geometry without using U substitution, without using the fundamental theorem of calculus. Well, the next one certainly will be done with U substitution. We have the integral of 5x squared times 2x cubed plus 7 to the 11th power dx. U is 2x cubed plus 7. Its derivative is 6x squared. This is some multiple of 6x squared, which is going to make this workable for us. So here's our process. U is 2x cubed plus 7. The derivative with respect to x of u is the derivative with respect to x of 2x cubed plus 7. The derivative with respect to x of u is du dx, and the derivative with respect to x of 2x cubed plus 7 is 6x squared. And I want to solve for dx, so we'll say du is 6x squared dx, and du divided by 6x squared is dx. Replace dx with du divided by 6x squared. Replace 2x cubed plus 7 with u, and see what happens. So we'll have 5x squared u to the 11th du over 6x squared. The x squareds cancel. 5 over 6, 5/6 comes out. And all we have is 5/6 integral of u to the 11th du, which is nice. There's only u's involved. That's our process. And of course, the integral of u to the 11th is u to the 12th over 12 with our power rule that we've seen in our earlier problems. 6 times 12 is 72. So we get 5 over 72 u to the 12th plus c, but not quite our final answer. We need to substitute u equals 2x cubed plus 7 to get our answer in terms of x. So our final answer here is 5 over 72, 2x cubed plus 7 to the 12th power plus c. Our next example is integral of 2x over x minus 5. This one is not obvious. We're going to let u equal the denominator x minus 5. Then the derivative with respect to x of u is the derivative with respect to x of x minus 5. Left-hand side is du dx, right-hand side is 1, therefore du equals dx. I have that substitution, and I have x minus 5 as u, but what about the x upstairs? Well, the answer to that is to recognize u equals x minus 5, so u plus 5 would have to equal x. It should be u plus 5. Let me go ahead and fix it. No, nothing quite to fix, actually. U plus 5 equals x. That's what we have next, and that's going to be our substitution. That x becomes u plus 5. So we have the integral of 2 times u plus 5 over u du. Distribute this u, 2u plus 10 over u du. Now I have a single denominator. I can rewrite it as 2u over u plus 10 over u. And 2u over u is just 2. So we have the integral of 2 plus 10 over u du. Integral of the sum is the sum of the integrals. Integral of 2 plus integral of 10 over u. Tell me a function whose derivative is 2 if u is the variable. It's 2u. The 10 will pull out in front. And the integral of 1 over u is natural log of the absolute value of u. So here's our 2u plus 10 times the natural log of the absolute value of u. Let's plug x minus 5 in for u here. And we can distribute this 2 to get 2x minus 10. And this answer is correct. We can make it a little cleaner by recognizing negative 10 is an arbitrary constant. So negative 10 plus this arbitrary constant is still an arbitrary constant. So the negative 10 in essence gets absorbed into that constant. So a better answer is 2x plus 10 times the natural log of the absolute value of x minus 5 plus c. Our next example is the integral of 7x squared over x cubed plus 1 dx. U will be x cubed plus 1. The derivative of that is 3x squared, and upstairs we see a multiple of that. That is our strategy of knowing there's a good chance u substitution is going to work. So u is x cubed plus 1. Derivative of u is derivative of x cubed plus 1. du dx equals 3x squared. I want to solve for dx. Multiply both sides by dx. du is 3x squared dx. Divide by 3x squared. Du divided by 3x squared is dx. This thing is u. We're going to leave 7x squared alone. So we'll have the integral of 7x squared over u times du over 3x squared. you will notice the x squareds cancel. 7 over 3 comes out as 7/3, integral of 1 over u du. And we know that is log absolute value of u plus c. What is u? U is x cubed plus 1. We get 7/3 log absolute x cubed plus 1 plus c. Our next example is the integral of 7 times sine to the 8th of x times cos x dx. This is the complex piece. U is going to be sine x, and its derivative is right there. Cos x is right there, so a multiple of that is present, so that U substitution has a chance to work. If I let U be sine x, the derivative of U is the derivative of sine x. So du dx is cos x. Multiplying both sides by dx, du is cos x dx. And then dividing by cos x, du divided by cos x will equal dx. This becomes 7 u to the 8th cos x times du over cos x. Again, sine x is u to the 8th, cos x stays from before, dx is du over cos x. Notice the cos x's cancel. We are just left with one variable, u, which is what we want. Pull the 7 out in front. 7 times the integral of u to the 8th du, 7u to the 9th over 9 plus c. But what is u? U is sine x. So 7/9 sine x to the 9th plus c. This notation works well with the graphing calculator. Typically textbooks prefer this notation, but they mean the same thing. Sine to the 9th x means quantity sine x to the 9th power. So our answer is 7/9 sine x quantity to the 9th plus c. And we have one more problem to do in this lesson. The integral from 1 to 2 of x times the square root of x squared plus 3 dx. So we have to worry about the endpoints. And we have a u of x squared plus 3 because its derivative 2x, a multiple of that is present on top. U is x squared plus 3. The derivative with respect to x of u is the derivative with respect to x of x squared plus 3. The derivative with respect to x of u, du dx equals 2x. So du is 2x dx, and then dividing by 2x, we get du divided by 2x is dx. That's going to substitute there. X squared plus 3 is going to be u. That x is going to cancel nicely, but we have to change our endpoints. This is x equals 1. That's x equals 2. So making our substitution, recognizing then that u is x squared plus 3, what will an x of 1 give me? 1 squared plus 3 is 4. We see that plugging the x of 1 into x squared plus 3, we get 1 squared plus 3 is 4. And now plugging in our x equals 2, what are we going to get? Same sort of deal. 2 squared is 4, 4 plus 3 is 7. We get our other endpoint is u is 7. So our lower endpoint is u is 4, our upper endpoint is u is 7. That's how we're going to change that. X square root of u, dx is du over 2x. So here's all the information we need. X equals 1 gives us u equals 4, x equals 2 gives us u equals 7. X times the square root of u, square root of x squared plus 3, dx is du over 2x. The x's cancel. The 1/2 goes out in front. And I have the integral as u goes from 4 to 7 of the square root of u du. And you can see we're just about finished. Root u is u to the 1/2 power. And then we remember our power rule. Integral of x to the n is x to the n plus 1 over n plus 1. That will be u to the 3/2 over 3/2 as u goes from 4 to 7. 1/2 divided by 3/2 is 1/2 times 2/3, or 1/3 u to the 3/2 as u goes from 4 to 7. So we're going to get 1/3 7 to the 3/2 minus 4 to the 3/2. 7 to the 3/2 is the square root of 7 cubed. So I'm going to use a calculator to help me out there. 7 cubed is 343. So we get 1/3 the square root of 343. Now how about 4 to the 3/2? 4 to the 1/2 is 2. 2 to the 3rd is 8. So 4 to the 3/2 is 8. And that will conclude this lesson.